This lesson is more on continuity, and this is kind of by itself because we're going to talk about the formal definition. The formal definition has the limit as you approach C from the left equaling the limit as you approach C from the right equaling f of C, which is the point. So some people tend to forget that, so that is the point. So think about what that means. That means if I have a graph and I'm approaching it from the left, that means I'm approaching the same place from the right, and f of C is the output of the point. That means the point is there. And so there is our continuity definition, just broken up into 3 parts. Now, here's the thing. If the directions are asking you to show, prove, explain, justify, or anything like that, you want to do all 3 parts. Even though it may seem monotonous because you're getting the same thing, you have to cover all 3 parts to get the credit for that type of problem. So here's my first example. Show that x squared minus 5 is continuous at x equals 2. That means I need to do the limit as x approaches 2 from the left of x squared minus 5, the limit as x approaches 2 from the right of x squared minus 5, and f of 2. So let's work these out. Obviously, 2 from the left and 2 from the right, if you can plug in and get an answer, that's the answer. So I'm going to plug in 2 squared minus 5. That'll be 4 minus 5, so I get negative 1. Again, from the right, it's the same deal. If I can plug in and get an answer, that's my answer. So 2 squared minus 5, again, negative 1. Now f of 2 means I plug in. So 2 squared minus 5 equals 1, negative 1. So I've done that work 3 times, but I have shown the 3 parts, okay? And this is the most simple example, but you'll see some in a minute that are a little more difficult, or not really difficult, but have some interesting parts to them. So we have example 2, and it asks, is this function, which is a piecewise function, continuous at 1? So again, I'm going to do the limit as x approaches 1 from the left, the limit as x approaches 1 from the right, and f of 1. So with a piecewise function, when I'm trying to determine the limit as we approach 1 from the left, I have to decide, well, which equation is on the left side of 1. So I come over here, x less than or equal to 1 is the left side, x greater than 1 is the right side. So for the left side, I'm plugging into x squared minus 3. So 1 squared minus 3 is going to be negative 2. And then for the next one, 1 from the right side of 1 is x is greater than 1. I'm going to be plugging into the bottom equation, so 2 times 1 minus 4. And again, I get a negative 2. With the f of 1, I have to decide where it is actually equal 1, and that is up here because that equals mark with the 1. So I'm plugging into the top formula. So 1 squared minus 3 again is negative 2. Since all of these match, they're all the same number, then f is continuous at 1. Okay, here's another example similar to that first one. Explain why f is continuous at 3. And when people get this type of thing on the AP exam, they've forgotten what I usually teach them right here, and they try to make up a paragraph trying to explain why it's continuous. But you really just need to hit those 3 points. The limit as x approaches 3 from the left of f of x, the limit as x approaches 3 from the right of f of x, and then f of 3. So I'm going to start, again, since this is not a piecewise function, we're plugging into the same thing, and if we get an answer that's okay, which we should because it's not a fraction, we won't get 0 on the bottom, that's our answer. So 2 times 3 squared plus 1, and that's going to give me 19. I'm getting that same thing here. And if I plug in to get the y value of the point, again, I'm plugging in doing the same exact work. But showing the work is your proof in why it's continuous. If you wanted to write a sentence, you could say, since the limit as x approaches 3 from the left of f of x is 19, the limit as x approaches 3 from the right of f of x is 19, and f of 3 is 19, the function is continuous at 3. And that would basically tell them everything we just did in a nice sentence. Okay, so this last example you might want to pause and try it for yourself. But otherwise, we're having another piecewise function, and they want to know if it is continuous at x equals 0. So I'm going to say the limit as x approaches 0 from the left, the limit as x approaches 0 from the right, and f of 0. So again, because it's piecewise, I have to figure out which side's the left and which side's the right. So less than 0 would be the left side. So I'm plugging in 0 plus 3, getting 3. And then 0 from the right, that would be the greater than 0. So 2 times 0, I get 0. And then f of 0 is where it actually equals 0. So that would be with this top part because of that equals mark. So 0 plus 3 would equal 3. Now, all of these don't match. So if you're explaining, is it continuous, I would say, first of all, no, it's not continuous. My explanation is that the limits on the left and the right don't match, because the limit on the left and the point match, but the left and right limits don't match. So I'm going to say, okay, since the limit as x approaches 0 from the left of f of x is not equal to the limit as x approaches 0 from the right of f of x, the function is not continuous. So I've zeroed in on the part that's not actually making it work. And that concludes this lesson.